Okay, so here we're going to we're going to start a new section called focusing on linear transformation. So we spent you a lot of time talking about vector spaces. So what we want to do here is how do we create a map between vector spaces, right? And we want that map to respect the structure that we have created with a vector space, and the vehicle for that is going to be a linear transformation. Right, so everything we have done here with the matrix multiplication, matrix vector products, these are all special cases of linear transformation. So what that means is we've already been doing these linear transformations, we just haven't called them that. Right, now first, what defines a linear transformation? So we're looking at a function, right, but not like an algebraic function like we're used to. Right, so we want a function between u and v. Right, so it's a function between two vector spaces. Two vector spaces. All right, now it must satisfy these two properties in order for it to be a linear transformation. All right, now the first one is additivity. So it must satisfy two properties. All right, so the first one being additivity. So T of u plus v is equal to T of u plus T plus v. And the second one is homogeneity. And this one is in regards to scalar multiplication. So T of alpha u is equal to alpha T of u. Right? Now, u, our subspace u, is what's called the domain. And v is called the codomain. All right, now sometimes referred to as the range, but the range are the actual elements that are mapped in V. Now, as we'll see later, sometimes it is not all of the elements in V, and sometimes it is, and sometimes the range does equal to the codomain. And sometimes it's not, right? Sometimes the range will just be a subset of the codomain. All right, so all that will come later when we talk about what's called injectivity and surjectivity. But for now, this is what our linear transformation is, right? So again, what you want to kind of get from this, right? So when we say something like, well, first of all here, right, if u and v, they are from our domain, right? So they are part of vector space u. And then the corresponding linear transformation, tu, tv, those are part of vector space v. Okay, so just keep that in mind here, right? That they are, the addition here is from two separate vector spaces, right? And we see this and this, right? This first one on the left here is addition in vector space u, and this one on here is addition in vector space v. Okay, which may look different, right? They might be different vector spaces of different dimension, right? So just keep that in mind, right? So what this is saying here is that you can add the additivity one, right? You can add the vectors in U and then map them onto V, or you can map the vectors individually from U to V and then do the addition in vector space V. And that should still, they should get the same value here. All right, so that's what this is stating here. And the same for the scalar multiplication, right? You could take a scalar multiple in U, the vector space U, and then transform it, or do the transformation and then multiply it by the scalar in vector space V. All right, so for example here, let's look at T be the transformation between R2 and R3. Well, it's defined like this, so usually we'll have a definition like this. Okay. All right, so if we look here, is this example of a linear transformation. All right, and here let's make sure that additivity is satisfied, so we can have like x be x1, x2, and then y be defined as y1, y2. And we want to say, all right, what does t of x plus y look like? All right, so that's t of x1, x2 plus y1, y2. So that's t of x1 plus x2 over, x1, y1, y2, x2, y2. All right, and then applying our rule here, right? So we have x plus 1 plus x plus 2. So we have x1, y1 plus x2 plus y2. And the other one is subtraction. And then we have 2x1 plus y1, right? Because again, right, the transformation is x1 is just element 1, x2 is element 2. So that's what it would look like for x plus y. So that's when we do the operation inside our vector space R2 and then map it onto R3. All right, so now let's take a look at this. So this one is asking me to do the transformation first. Okay, and then add the vectors, right? So here, if I do that, then we got x1 plus x2 and x1 minus x2 over 2x1 here. x1, oh, excuse me, y1 plus y2, y1 minus y2 over 2 y1. All right, and now we do the addition here in R3 to get the vector x1 plus x2 plus y1 plus y2. And then here, rearranging this, we see we have x1 plus y1 minus x2 plus y2. And twice factoring x1 plus y1. And we see that the structure holds, right? It's the same. Doesn't matter when I do that addition, right? Inside R2 or inside R3. All right, and the same for our scalar multiplication, right? So if we do alpha x1, x2, we get t. Oh. right, looks like I'm having technical difficulties, so I'm gonna pause here, and then we'll pick this up in a bit.